Now that we've looked at the basic idea of the electric field, we'll look specifically at the electric field of a point charge. Now, if the electric field is just the electric force divided by that test charge, Q test, for a point charge, we can substitute the electric force as K times Q of the source times the test charge, Q test, divided by the distance between them. In this case, I'll call it RST because it's the distance between the source and the test charge, and then that is squared. And the direction, remember, is attractive if they're opposite charges, and it's repulsive if they're the same, if they're like charges. So if we take this equation, Fe, and divide out Q test, what we end up with is an expression for the electric field for a point charge of E is equal to K times Q source. Often we just call that Q over R squared. And the electric field direction is towards the source charge if the source charge is negative, and it's away from the source charge if the source charge is positive. Then if we recall that the electric force on the test charge, so I'm going to call that F of t, it's the force on the test charge, is equal to the test charge times the electric field at a given point. Because of that, I can say, therefore, if the test charge is positive, then the force on the test charge will be in the same direction as the electric field. If the test charge is negative, then the force Ft on the test charge will be in the opposite direction to the electric field. And because this is vector math, those directions actually come out of the math. If you have a negative number times E, then F of t will be in the opposite direction to the E, the electric field vector. For example, if the electric field at a given point is 3 I hat newtons per coulomb, then I can have Q1 at that point, and the force on Q1 at that point would be equal to Q1 times E. If Q1 is actually, I'll give it a number, say 2 microcoulombs, so positive 2. Then I would actually substitute in positive 2 microcoulombs times 3 I hat newtons per coulomb, and I would actually get then 6 times 10 to the negative 6 I hat newtons. So that's 2 times 3 times the micro, which is 10 to the negative 6, and that would be Q times E. If I have a negative charge, Q2, that's equal to negative 4, say, nanocoulombs, just to switch things up. Woo. Anyway, at that point then, if I want to solve for F on 2, at that same point in the electric field, I'd have Q2 times E, and when I substitute in, I'll have negative 4 nanocoulombs times 3 I hat newtons per coulomb, and I would end up with negative 12 times 10 to the negative 9 because it's nano newtons for the force, and the direction is going to be I hat. Now, that means that, remember, F1 on the positive charge has a positive number, 6 times 10 to the negative 6 I hat. It's in the same direction as E. Q2 is negative, and when I multiply it out just from the math, I get that F2 is in the opposite direction. Okay, so there are some key points to summarize about electric fields up to this point. The first one is that changing the test charge will not change the electric field. With the analogy to the gravitational field, that's like saying if I throw a ping pong ball versus a textbook, I don't know why you'd throw a textbook, maybe. Anyway, changing the test mass that I'm throwing does not change the gravitational field. And so for electricity, changing the test charge will not change the electric field. Changing the test charge will change the electric force, however. And from the analogy for gravity, that's just like saying that the ping pong ball and the textbook each have a different force of gravity because they have different masses. So changing your charge, Q1 and Q2, would have different electric forces because they have different charges. The third point is that the electric field is not a force. Yes, it is a vector, but it is not a force. We have to multiply it by the charge. Remember, the units for electric field are newtons per coulomb, so we have to multiply by coulombs before we can actually get newtons to get the force. The fourth point is that the electric force on the test charge depends on the test charge on QT, but the electric field will exist even if QT goes missing, if we take it away. And the last key point is a quick summary right here. If we have multiple point charges as sources, then the net electric field is just the vector sum of the individual electric fields from each point charge. And I'll just expand on that a little bit here with a quick example. So for example, if we have a positive charge here, Q1, and a negative charge over to the right, Q2, and then another negative charge, I guess I'll put that on the bottom left, Q3, then I can maybe ask for the magnitudes and directions, maybe not the magnitudes, just the directions, because I don't want to do any math for this. I'll choose a point partway down from Q2 and call that point P. So at point P, I'm going to have 3 individual electric fields, one for each point charge. But remember, the definition of a field is a region that has a unique value at each point. So I can't really have 3 different values. What I really get is the net value, and the electric field is a vector quantity, so I can just add that up. So if I start with the first one, Q1, the electric field for Q1 is going to point away from the positive charge. So I'll show that as a direction like that, and I'll just call that E1. Then for Q2, it's going to go towards that point charge. And I'm going to imagine that these charges all have the same charge. So Q1, the magnitude of Q1 is equal to the magnitude of Q2, and that's equal to the magnitude of Q3. And I'll just try to show that the magnitude of E2 is actually also bigger. And that's because point P is closer to Q2 than it is to Q1. And so even though the charges have the same magnitude and the K constant is the same in each case, when you divide by R squared, because R is smaller, you get a smaller denominator, which gives you a larger overall value. So the last one is Q3. Now, point P is farther from Q3 than it is from Q2 and a little bit closer than E1, so it should be somewhere in the middle. I'm not going to stress too much about getting the exact vector lengths. I'm just trying to introduce the idea. So out of this, we have 3 different vectors. To get the vector sum, we just have to add these up. Okay, so adding up first E1, then E2, then E3 gives me a net electric field going from P to the tip of the red vector there, and that would be E net. And that's considering the effects from all 3 point charges, Q1, Q2, and Q3. By this point in the course, you've probably already had to work with vectors a lot, and it's not going away. In fact, later in the course, we end up working in 3 dimensions because you just can't get away from that. And you might already be doing that depending on where you're taking this course. So if you're struggling at all with vectors, one of the most important things I can tell you is to try to master the vector math as soon as possible. If the vector math is as simple to you as using a pencil, then you're going to be golden. But if not, then it's really worth investing some time up front so that by the time you get to quizzes and tests and exams, you're not thinking about the mechanics of the vector math, and it gives you more time so that you can actually think about the difficult problems. The last thing to note about the electric field of a point charge is that there's an alternate notation using a unit vector r hat. And this is similar to the Coulomb's law notation that uses r hat. And the big difference is that we have our electric field now, and because it's the electric field and not the force, we only have one charge, so we're just talking about this for the point charge. Divide that by r squared, and then we multiply by r hat. And in this case, r hat is always pointing away from Q. Now you probably remember from the example that we just looked at that in some cases, for negative charges, the electric field points towards the negative charge. And the way this works then, if, for example, we have a positive charge and then we have r hat as a vector, then the part in the middle, kq over r squared, will be positive. And that gets multiplied by r hat, and then you'll get a value for the electric field at some point. If you have a negative charge, negative point charge, then r hat again points away. When you multiply k and then q, and q is going to be a negative number, divide by r squared, everything in the brackets here is going to be negative. So when you actually have solved for the electric field vector, you have a negative number times the r hat, which means that the electric field is going to be going in the opposite direction, towards the point charge. So this convention might actually be preferable for you. It has the advantage that the r hat is always away and the direction just comes out of the math. I don't think either approach is necessarily better than the others, so I would suggest that you just choose whichever makes sense to you and stick with that.